So for chapter 7, we start off with talking about the basics of all chemistry, what makes up an atom. Inside an atom, right smack dab in the middle, we have our hard, dense nucleus, where 99% of our mass comes from. That is made up of our protons and our neutrons. One of the main roles of the neutron is to make the nucleus possible. If the nucleus were just protons, all massed together, positives repel. The entire nucleus would repel itself and therefore combust. It wouldn't be able to hold together as a nucleus. Having these neutral balls in between each of our protons actually allows them to be arranged in this very dense structure, even though they have this positive charge. Okay? Now, the electrons, we know that they orbit around the nucleus. However, most models show this inaccurately. This model is, of course, inaccurate because it doesn't show energy levels. This model is inaccurate because it doesn't show them orbiting, especially in different arrangements or in SPDs or Fs. Being able to identify a weakness in a model is very crucial. Very often on the AP test, there will be something where they give you a picture, they give you a model. You identify what is good about that model, what is bad about that model. What does it depict correctly? What does it depict incorrectly? Okay. So this model here, it depicts energy levels, it depicts orbiting, but it also doesn't depict SPD and F. This one, you can't really tell. I think that this is an orbital and that's an orbital. A strength on this one is the way it shows electrons. Electrons aren't really just solid little balls. Quantum mechanics is wherever we start looking at electrons more like waves. They are in such constant motion at such high speeds. You now consider them more like a wave instead of an actual particle. Think about the blades on a fan going 1,000,000 miles per hour. You could no longer dissociate where exactly a blade is, or really even consider it as being an individual substance. Those blades now are working together as a unified wave, and that's what's going to be created. Now, another thing is the fact that these electrons are in motion is the only reason why the atom can exist as it does. 99% of the volume of an atom comes from the electrons. We have a teeny, teeny, tiny nucleus. If we had a football field as our atom, our nucleus would be a P at the 50-yard line. The rest of that would be the volume of the electrons. Now, the size of the electron isn't even imaginable even if you were able to blow an atom up to the size of a football field. So when we're talking about how minuscule the mass is of an electron, you still can't imagine it on a football field scaled analogy, because the nucleus is still only a P inside a football field. Okay? Now, these electrons, this constant motion, is the reason why the atom exists. If they were not in constant motion, this positive nucleus and these negative electrons, this pull between these two, would cause the atom to implode. Okay? These electrons being in constant motion is what enables them to keep a shape, enables them to resist the pull of this positive nucleus. Now, this positive nucleus plays a huge role in everything we're going to be talking about, but this constant motion is also just as important. If they're not in motion, they would combust. The amount of speed of that motion is their energy, that's their kinetic energy. Lower energy electrons are going to be as close to this nucleus as possible because they are able to resist this pull the least amount. So the lowest the energy, the closest to the nucleus. They can resist the least. The higher the energy, the further away from the nucleus. They're not having such a strong pull into this nucleus. So how do these electrons orbit? Well, they orbit in set areas. Okay, we can see this with 3D microscopes. These set areas have set shapes, and they always orbit in maximum groups of 2. Which makes sense. They're electrons, they're negative, they repulse one another. So we can't really combine electrons in dense arrangements around each other. They'll just push each other out. The best we can do is have 2 electrons using the same orbital and going in opposite directions. That way they don't repulse one another out of the orbital. We'll discuss that a lot. So right here we have electron microscopes. They actually give us a 3D representation if we're able to use waves to try and visualize what is happening inside of the atom. That's how we got these shapes of SPDs and Fs. So looking at this 3D representation of a true atom, this dense part right here would be what orbital? An S, because we have this circular shape. And these extensions following along the X, Y, Z, and the X, Y, and Z axis would be. Now we have another representation. This is a different type of machine that tries to give us a picture of what's happening inside the element. And you can see they actually wrote little tiny p's where the p orbitals would be from different elements. Because of these, we end up with these pictures for each one of our different orbitals. An s orbital always has this circular shape. It is always the closest suborbital of an energy level. It's closest to the nucleus, it has the lowest energy. And it follows just this very concise circular path. A p has an x, y, and z. If you notice, the densest areas are going to be at the very end. This is the highest probability that an electron will be here. Okay, our D's and our F's, there's debate over their shapes. There's actually a lot of debate when it comes to D's and F's. But in general, if you were to combine all of these very odd shapes that the D's and F's pull, if you were to combine them together, if you were to combine all of these orbitals together, you end up with a circular shape. That's where this energy level comes from. So although the Bohr models of having a nucleus with circular energy levels around it is inaccurate, it could be a condensed version of the SPD and F, because for each one of these, the highest probability of the electron is on the furthest outermost point of that energy level. So the highest probability of electrons is at this circular shape for each energy level. And between each of these orbitals are areas where there are no electrons ever. And we call those nodes. Okay. Now, this arrangement of electrons in SPD and F, this has to do with quantum mechanics. Quantum mechanics has many, many, many scientists you've heard of involved with it, like Schrödinger and Heisenberg and Einstein. Although quantum mechanics is very, very complicated, very complex, and entirely different from everything else, anything had ever been discovered in science. So much so that even though Einstein was one of the main discoverers, main supporters, and showed all the math to support it, he then spent the next 20 years into his deathbed trying to disprove it. He did not like quantum mechanics because it is such a complex and absurd concept. Here's an example. If I take two electrons under the exact same situation, shoot them in the exact same direction, everything is held constant. Nothing is changed. If they were two bullets, they'd land in the exact same place. Two electrons don't. They don't land in two different places and continually land in two different places. They land in an absurd amount of different places. They can continually test this over and over and over again, and there's not a statistical significance of, okay, the first time it will always land here, the second time it will land here. It's not statistically accurate or able to be predicted. It is very complex, high levels of chemistry and science. That's where you get the theories from like Schrödinger and Heisenberg. Schrödinger's cat theory, that was his way of trying to explain it. If I put a cat in a box with a vial of poison, that will explode based off of a radioactive isotope. So we have no idea when it will explode. When that vial explodes, the cat will die, for sure. However, if that box is closed, I have no idea if that vial has exploded or not. Therefore, there is a 50-50 shot, equal probability that the cat is both dead and alive right now. Everyone could say one or the other, and there's no way to prove it until you open the box. This is what this Schrödinger's uncertainty principle is. It is entirely uncertain where this electron would really be. And that's what these probabilities of electrons come from, in this uncertainty. I cannot know how fast an electron is going and where it is going at the same time. I can know either or. If I know where an electron is, that means I stopped it moving. Then I don't know how fast it's going. If I know how fast it's going, I have no idea where. I can have a general area. That's what these shapes are. So each one of these SPD and F shapes are a general idea of where that electron is going, and I know it's going at a certain speed in this general area, no idea where. Same thing if I go look up your house. I can find your address, see where you live. I have no idea where you live in that house. You are somewhere in there. I know that each of these electrons live in this orbital, no idea where in that orbital they are at that exact moment. Okay? So electron configurations try and give us that location of the electron. We can get a location, a general spot where it lives in its orbital. So from our electron configuration, we're talking about our energy levels and our sublevels, right? When we write our electron configuration, we write it so we have our energy level in front, the type of orbital here, and the number of electrons on top. That's for each one. We continue that throughout, write all of our directions all the way to the element. Now, our Aufbau principle, okay, his name is Aufbau. Aufbau said we fill our energy levels, the lowest energy level first. Okay, so if I take all of my energy levels and I show you how much energy they have, energy is increasing going up this. We fill our first energy level, our second, our third, our fourth. That makes sense. I said that our lowest energy electrons live closest to the nucleus because they're able to resist the pull of the nucleus the least, right? If you're not able to resist the pull, you're very at low energy, they're going to get pulled in the closest possible. So our lowest energy level electrons are here, and Aufbau says we fill the lowest first. 1, 2, 3, what? Now what happened here? Well, when you write your electron configuration, up to this point, you've just written it the way the periodic table says to. And it says to go 4s, 3d. Now y has to do with those shapes. Okay? When we're at 3p, the next energy level that's physically closest is actually 4s. Because 3D has this weird, crazy, wonky shape that goes crazy far away from the nucleus and close. So because the crazy shape of the D, here's my nucleus, the orbital goes really far away, my 4s actually starts before my 3D ends. And if electrons are going to be as close to the nucleus as possible, if they're going to go to the lowest energy level possible, then my 4s is actually lower, even though it's in 4, it's actually closer physically to the nucleus than my 3D. So because of that, they fill the 4s, then the 3D. Because the 3D ends up being physically further away from the nucleus, even though it's still part. This red would be still part. Here's 3s, here's a 3p, okay, a 3f. All the red would still be 3. But because the D is so huge, it ends up extending past the 4s, so we'll fill the 4s first. F is even larger. It ends up extending past 2 s's before it ends. That's why when you're following on the periodic table, I'll shrink this one and get rid of it. When you're following on the periodic table, we go 6s and then 4f. Because the F, even though it's all the way from our 4, it ends up filling in a different order. Okay, so following the periodic table, you're going to write them the way that they fill. Okay. Now, I made sure to represent this periodic table on here because this is how the periodic table should look. There's absolutely no reason for us to print it like this, though, because then each box would be teeny tiny and we couldn't see it. So we do not print it like this. We print it like this. But you do need to understand that this F box belongs here. Okay? So because our F box belongs here, we do write our periodic table, we write our electron configurations the same way that they're represented on this periodic table. Now, in our depiction, once again, a weakness that we can find in this model, this is an easy way of seeing each of our 7 energy levels. You see which of our sub-levels exist on each one of these. However, notice in this it says 7s is furthest away, not so much. Okay, so that'd be a weakness here. That also has it on a very 2D flat structure, none of the shapes are there. But this is one way of depicting, okay, if I have an energy level, it does get subdivided into sub-levels. Each sub-level of S, P, D, and F is made of orbitals. My s sublevel has one orbital. Each orbital holds 2 electrons, so each s can hold 2 electrons because it has one orbital. A p can hold 6 electrons, therefore it has 3 possible orbitals, 3 possible locations for electrons to live, each of which can live in maximum of 2 electrons because of the repulsion. D, 10 total electrons, so 5 possible orbitals. F, 14 total electrons, 7 possible orbitals. A regular electron configuration only includes energy level and sublevel. 1s2, and then 2s2, and then 2p6. It doesn't say which of the orbitals inside p is being used, it just says all 6. So an orbital diagram actually shows each orbital inside the subshell. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. I have 3 electrons out of the 5 possible orbitals of d. Now the way these are filled in follow 2 specific principles. Well, actually 3 if we include our original. Aufbau. Aufbau first. Aufbau, once again, fill the lowest energy level first. Second, we have Hund. For Hund, think of your hand. You can spread out your fingers as much as physically possible. Okay? Your electrons will spread out as much as physically possible within a subshell. Aufbau says they're going to fill the lowest first. But when they're within that lowest, they'll spread out as much as possible. So if I have to put 6 electrons in a p, well, p has 3 orbital. Notice sometimes they draw lines instead of boxes. So I have 3 possible locations for these electrons. The first 3 will spread out, then you will fill with the next 3. So correct, 1s2, 2s2, 2p2. Okay? This one is spread out as much as possible. These 2 will not combine together while there is still empty space. Which makes sense, they're electrons, they repulse. If these 2 tried to combine together, while there's an empty spot right here, this one will push that electron into the empty orbital. It's just physically impossible if there's an empty orbital to try and double up on 2 electrons here. So that's Hund, hand, they spread out. Pauli says that when they do have to double up, they will go in opposite directions. Okay? So by the way, this little picture here is correct for Pauli. It's wrong for Hund, right? And I'm going to go through several examples of each one, how each one applies. You need to know all 3 of these, how they apply, and be able to recognize them. So for example 1, who did I break? Pauli, Hund, or Aufbau? We broke Hund. This one should have gone into its most spread out form, should have gone to the empty orbital. Example 2, did we break any rules? We broke Aufbau. Aufbau said we're going to fill the lowest first, so we should have doubled up because of Pauli in 2s before going into 2p. So did we break any rules on 3? No. We have Aufbau is correct. We filled our 1s and our 2s before filling 2p. For Hund, we spread out as much as we possibly could. And for Pauli, when we did have to double up, we spun in opposite directions. Lastly, example 4, did we break anyone's rules? For example 4, we broke 2 rules. We followed Aufbau. We did fill 1s, 2s, and then 2p. But then for Hund, we didn't spread out as much as we possibly could. This one should have gone up. And then for Pauli, when we did double up, we should have gone in opposite directions. For the electromagnetic spectrum, I do not expect you to know the entire spectrum. I expect you to use the knowledge you already have. Everyone knows Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. If you know Roy G. Biv, you should know where infrared is located. After all, it is right beside red, and ultraviolet is right beside violet. You also know, based off of flame color that you learned when you were very little, about which flame has the most energy. Blue. Blue is a higher energy than a red or an orange or a yellow flame, which means that my highest energy is in this direction. So protons and their positive pull on electrons. Protons play a huge role in the entire relationship of your size, your trends, everything. This attraction between protons and electrons is very important. So on the periodic table, anytime we say something is a neutral atom, which all atoms are on the periodic table, because we're not talking about ions on the periodic table, a neutral atom means each new element has added a proton. If we add a proton and it is still called neutral, then we have also added an electron. But having an equal number of protons and electrons does not mean an equal pull because of the location of the electron. The location of the electron is going to have a very big role on this effective pull from the protons. Now Z is always the symbol of proton. It's always the symbol for your atomic number. Therefore, Z with a little under subscript of F means effective proton pull. Okay, so your Zeph, and that's very important, and you'll use this symbol whenever you see it. Our core versus our valence electrons, think of an apple. Core electrons are in the core of the apple. They're the closest to the nucleus. They are held the strongest. They are going to be the hardest to get rid of by far. The valence electrons are the furthest out, and because of that, there are things playing a role between their relationship and the nucleus. So the first thing I want to do is look at this picture here. This picture here gives us a depiction of a 2s or a 1s through a 3s. So it's very hard to depict these, but this would be a pretty real example of that. We have a 1s in the center. Right here, there's only 2 electrons in there. Those 2 electrons are going to be held stronger than anything else. Helium, right, a noble gas, trying to take an electron from that is going to be ridiculously difficult. Going on to your 2s, there are 2 electrons here. Now these electrons here, they're actually being blocked. These electrons here, the pull of the nucleus is actually slightly blocked by the 1s. Okay? So think about this. Let's look at these planets. If we think about the orbital of planets, it kind of helps because that is a relationship to our solar system, to electrons. Our planets are in constant motion. The reason why they're not being pulled closer to one another by gravity and magnetic pull are very similar. The reason why our planets are not being pulled closer to each other, the reason why the moon is not coming and crashing into us, even though Earth has all of this gravitational pull, is because the moon has a constant orbit. It has this constant energy that's keeping it in a circular motion around the Earth instead of crashing into the Earth. Electrons do the same thing. They're in this constant motion around the nucleus. So if we imagine this, anytime we ever have an eclipse, we're having interference between the energy of our nucleus, the sun, and us. We're Earth. Anytime that our moon goes in between us and our sun, we get a visual representation of that less energy, right? The sunlight gets blocked. Same thing happens with an electron. Okay. If I have this electron here on my 2s, and one of my electrons on 1s goes in the direct path between it and the nucleus, and actually interferes with that attractive pull. Now, the further out we get, and the faster these electrons are moving, right, higher energy, the more often they're crossing each other's path. The more often they're, quote-unquote, blocking the sunlight, right? They're blocking that energy pull from the nucleus. That is shielding. They are creating a physical shield between that outer electron and that inner proton pull. They are literally going in front. They are causing a shield effect between. Because these electrons are moving at 1,000,000 times faster than the planets, these quote-unquote eclipses are happening over and over and over again. They're constantly creating this deteriorated pull from this positive nucleus. So that's shielding from previous electrons. However, electrons of the same energy level do nothing to pull away from the nucleus. So if I have an electron here on 3s, and I have an electron here on 3s, neither one of these are blocking the pull of electrons, or the pull of the protons on the electrons, right? So even though we're on 3s, there's some interference from our shielding. But on the same energy level, these two are not blocking the pull of the protons. So if we're on 3s, we now have 12 electrons. Okay? 10 are in here, sometimes blocking from shielding. But there are 12 protons in here, and this electron is not interfering with this. Okay? We got 12 protons here. This is my 11th electron. This electron doesn't bother blocking this off. As I continue across a period, I'm adding more and more protons. This pull is getting stronger and stronger and stronger. But as I go across a period, those electrons on the same energy level are not shielding each other. They're not causing interference between that outermost electron and the inner nucleus, which means this positive pull becomes more effective. Okay? If I was to add on my 3p out here, okay, the other 3p's, this one and this one, they're not blocking each other. So right now I have 2 more protons in there, and yet nothing is hindering that proton pull anymore. So what we just showed is that going across, okay, going across here, my effective pull gets a lot stronger because we're on the same energy level. So my protons are increasing going across, and electrons on the same energy level don't really interfere with that pull of the protons. There are 2 slight exceptions. Okay, right here after 2a. Okay. After 2a is when we fill the S and start the P. Part of the P of that energy level goes outside of the S. Just slightly, right? So if I have a shape here, like you see, I'll zoom in. When I'm on the 2, here's my S. Part of the 2p goes within the S. Part of the 2p goes without the S. So when you fill the S, when we start our 3p, the 3s can have some shielding. Not much, but some. So that's where that first exception comes from, is that right after 2a and when you start 3a, when you start your 3p, there might be a little shielding. So our Zeph has like a tiny little stumble here. We have one more stumble. At the end of 5a, okay, when I'm filling these orbitals, I got my 1 3p, my second one, and my third one. Remember, it's hard to draw in the 2D world. Remember, this is X, Y, and Z. Once I have these 3, and I have 1 electron in each, when I add the second electron, as I add the next electron into the same orbital, there will be slight repulsion. And because of that, that pulls away from that pull a little. Okay, so they're just 2 tiny stumbles. The overall effect is still the same. It still increases here. But right here, when I add a second electron into a P, because I have to double up, you follow Pauli, and they spin in opposite directions. When you double up, this causes a little bit of repulsion, which pulls it in just a little bit less into those protons. Because now, although there's still a really strong effective pull, although we've still added our protons, right here, that repulsion is going to push them away from each other, which also pushes them a little bit away from that nucleus. These are the only 2 exceptions to that, and most of the time you don't even need to realize those. There might be some times when you're asked, if you're given data, explain why my effective nuclear charge diminishes slightly from 2a to 3a. You would just say the complete S might create some shielding. So to justify and explain a periodic trend, you must always use these 3. Although I've taught you the arrows for trends work really well for multiple choice questions. You could easily deduct who has a higher electronegativity. Do not ever write those arrows on a free response question. Do not ever say, so-and-so is higher on the arrow than so-and-so. That makes no scientific sense. The arrow is a general, just statistical trend that means nothing. If they say justify or explain, that means give them some science. The science comes from the fact that Zeph increases going across because of the addition of protons with less shielding, right? The distance of the electron from the nucleus, think about two magnets. The further you get them away from each other, the less they attract one another. And then shielding. If I have two magnets pulled away from each other and I start putting pieces of magnet in between them, the two extreme magnets, the nucleus in the middle and the most valence electron, are going to have a lot less attraction to one another because there's interference from all the other magnets in between them. Okay, so Zeph, distance, and shielding. So let's apply this to ionization energy. Now we learned that overall, my trend is I go all the way up to helium with this. Ionization energy is the energy required to remove an electron. If I'm removing an electron, I'm creating a cation. Okay, this will increase going across because Zeph, as I go across, that effective nuclear charge is higher. These protons are holding on to these electrons a lot harder than they're holding on to these. So going across Zeph. Going down, each time I go down, I'm adding an entire energy level between that valence electron and that nucleus, which means I'm adding 8 or 18 or 32 electrons between that valence electron and that nucleus. That's going to create a lot of shielding, so distance and shielding. Going down, distance and shielding, going across Zeph. Right? That's what creates this overall trend. Helium is going to be the hardest element to take an electron from. It has 2 protons, and its only 2 electrons are right beside the nucleus. Okay? This is going to be held by far the strongest. The 2 exceptions fall under the exact same point. You could actually put the 2A exception here or here, wherever you want it. Okay, so if I have my exception here, once again for ionization energy, it will be easier to take 1 electron from the 1 electron that's in a P than it would be to take 1 electron from a full S. So there's a slight dip in ionization energy here. Same thing here. Because of the slight repulsion, anytime we're talking about an exception that happens right here, it's because of the new slight repulsion, because we went and added a second electron into that orbital. That new slight repulsion makes it a little bit easier to take an electron from oxygen than it would be from nitrogen. So overall, my trend going across still increases, but I get a little tiny stumble after beryllium and a little tiny stumble after nitrogen, and explaining this exception has been on the AP test like 14 times. So specifically, work on understanding this exception. Now, one last thing. This is first ionization energy, the energy required to take the first electron. Once you take that electron, you need to assess everything brand new. The arrow no longer works. Lithium, you take its electron, now it only has 1 energy level with 2 electrons on it right beside the nucleus. And it also has 3 protons. This is a lot stronger at holding on than even helium now. Beryllium, once you take 1, it's still capable of losing 1 more before you go down an entire energy level. Hence why lithium goes +1 and beryllium goes +2. So after that, you must consider the protons. Here's a visual representation of the first ionization energies once again, and crazy increase, but you see these little tiny stumbles between beryllium and boron, nitrogen and oxygen. And that stumble follows along the entire trend. For electronegativity and electron affinity, they're pretty much the exact same thing, but they're defined differently. One is the amount of energy either gained or lost whenever an electron is added. Electronegativity is the ability to attract an electron. So they're both relating to that addition of a new electron. They both follow the exact same trend. They go all the way up and end at fluorine because my noble gases are incapable of adding an electron or attracting another electron. There's 0 empty spots. Every single spot is full. So because these are entirely unable to attract, the trend ends with them. You don't really need to know the exceptions. You don't really need to know the exceptions. Atomic radius is measured as the distance between the nuclei of 2 identical atoms. So if I take F2, which is right beside itself, and I can see the nucleus of each very easily, very, very dense dark spot on a picture. Okay, compare the distance between the 2, halfway between must be how wide each of these atoms are. Now, the atomic radius, when you first look at it, seems kind of odd because it gets smaller going in this direction. But now that we know effective nuclear charge, that should make sense. even though mass is increasing here, mass increasing only means that we're adding more protons, which doesn't affect the volume at all. It doesn't affect how wide it is. But by adding more protons, that effective pull becomes stronger and stronger, and it's able to literally pull the electrons in closer and closer and closer. So going across, atomic radius gets a lot smaller. Going down, we're adding an entire energy level. We're adding a whole other ring. It's going to get fatter. And lastly, ionic radius. A cation is always smaller than the atom from which it is formed. Why? Because it lost an entire energy level. Li plus 1 means it lost the electron on its 2s and it only has one energy level. Be plus 2 means it lost its entire energy level and now it only has one energy level. That applies to all cations. They lose electrons until they lose that entire outer energy level. If you lose an entire outer energy level, you're a lot smaller. You also have more protons compared to your number of electrons, and everything is going to get pulled in a lot more. Anions are the exact opposite. We now have more electrons than we do protons. That proton pull becomes less. It's able to pull in the radius by less. Therefore, for an anion, it is always larger than the atom.